Hi, everyone. Good evening. I'm going to be talking, as Jun said, on mixing segregation and dry powder coating in an agitated vessel. And that vessel is the FT4 powderiometer that many of you may be already familiar with. Dry powder coating is a means of improving the flowability of powders by adding fines to reduce van der Waals interactions. Now, this means we're introducing some very fine material to mix with some coarser material, and that obviously means there's the risk of segregation as well. So this is the link between the two. So the first half I'll be talking about mixing and segregation, and then in the second half I'll talk about dry powder coating. The mixing research that we've done in our group was using the FT4, as I mentioned. For anyone that's not familiar, this device has got a twisted blade that is designed to ensure a constant shear stress across the blade. And our previous simulations have shown that it does indeed do that. This blade is rotated as it's driven down through a powder bed. And this is done to measure the flowability of that powder bed. So if it measures a higher torque, that means there's more resistance to flow, so the powder is more cohesive. It can be operated at various speeds. You can also introduce air through the base as well. So it's quite a flexible device. We've also used a modified vessel. Normally it's just a cylinder, about 50 mil internal diameter, 80 millimeter powder bed height, and we've added a sectioned vessel to this. So rather than the 80 mil height, we have 8 10 millimeter sections that we place on top of each other. We clamp them together, and that forms our vessel that we then pour powder into. And the reason we do this is because it means we can mix powders that differ in properties. Either they may have a density ratio, or they may have a size ratio. And then after we've mixed them for a certain amount of time, we can then take each section off at a time and quantify how much of each component we've got in that section, so we can determine the mixing index. When we're looking at a density ratio, it's percolation in both cases that's driving this mixing and then eventually segregation. So if the denser material is on top, it will gradually propagate down through the lighter material. So we place it in this arrangement. If we're looking at a size ratio, we put the fines on top so they can percolate through the gaps of the course and then lead to a more mixed structure. And once we've carried out a number of mixing test cycles, which is where we move this blade down and back up through the bed, we class that as one test cycle. Once we've done that, we take each section off in turn, and we want to find the volume of the fine or the light particles. From that, we can find the volume fraction of the other material. And the way we quantify the mixing index is by first determining the variance, which is the volume fraction of this particular component, the fine or light material, compared to the volume fraction of that component throughout the entire mixture, divided by the number of sections we've got, which is 8 in this case, and this difference is squared, as you can see. And then we're using Lacey's mixing index, which is the most widely used, very common mixing index for quantifying the degree of mixing. And this looks at two extremes. It compares the actual variance in the system. See, actually, I've changed symbol here. I use sigma and I've used S below. These are synonymous with each other. So this is the variance squared here. And S0 is this variance in the worst case. So if the system was fully segregated, the variance would be defined by just the fraction of that material in the entire mixture. And then SR squared is the variance for a random mixture, which is the best quality mixture that we can realistically achieve. So this depends on the number of particles within one of these sections, which we can determine since we know the size of each individual particle. So the mixing index is just comparing the worst case of variance to the actual variance we've measured and dividing by the difference between the worst and the best case variance we could achieve. So this always gives us a value between 0 and 1, 0 meaning it's not mixed at all, 1 meaning it's perfectly mixed or randomly mixed has been achieved. So we're looking for a higher value of M. So we do this After repeating tests at differing numbers of test cycles, each time starting with a new fresh bed, changing the number of test cycles we do, and then quantifying the mixing index. So if we look at these two combinations of glass beads we've used of these size ranges, this gives a size ratio of 4. On this plot, we're looking at the fraction of the fine material that is in each of these sections. So you can see there are 8 data points. These represent each of the 8 sections, and this is the height divided by the maximum height. So this is the top position in the bed. And we've got series for different numbers of test cycles. So initially, at 1 test cycle, all of the fines are present at the top. We've got none in the bottom. And then as we increase the number of test cycles, more of these fines move downwards and we get closer to a more uniform mixture, as you can see here after 20 test cycles. By looking at the mixing index, using the equations on the previous slide, we can see how this varies with the number of test cycles, and we can find it fits nicely to this equation here, where beta is a indicator of the mixing rate. A higher value means it mixes faster, and T is the number of test cycles. So plotted here, you can see the red triangles are this size ratio of 4 that I just talked about on the left. We also looked at a size ratio of 2, so we just doubled the size of these fines here. And then we've also looked at a case, let me just step back a moment. So these 2 cases, we've put the fines on top, we've put the coarse on the bottom, so we've initially segregated them. We then also looked at a case where we mixed the material together as well as we could using a tubular mixer, which is a tumbler mixer that rotates in 3 different axes to give a good quality mixing. And we found actually when we pre-mixed the material and then varied the number of test cycles, we didn't observe any segregation after 20 test cycles. But it may be that it just needs a lot more mixing before we actually see any segregation occurring. So these are plotted here. Now that's really as far as we went with the experiments. Those were using just plain glass beads. There was no cohesion introduced. You could introduce cohesion by adding silinization, for example, to coat and vary the cohesive interaction between the particles. But we thought it would be easier to analyze the influence of cohesion using DEM. I'm going to assume that people in the audience are familiar with DEM, but if anyone isn't, I can give a bit more background on that. But it really just is a means of simulating particles to see how particle properties and systems influence their behavior. So in the DEM, we've used the same arrangement of fines on top of the coarse material in this FT4 rheometer, but we're using larger particles so that the simulations don't take too long. And we've looked again at these size ratios of 4 and 2. And for a size ratio of 2, we've looked at 2 different combinations of 4 and 2 millimeters and 2 and 1 millimeters. So we make the system cohesive by introducing a surface energy. Sorry, I'm just seeing a question there from Mustaba. Is this something? Should I just leave the questions for the end? Is that best? I'll carry on. So the system is made cohesive by using the JKR contact model to introduce surface energy, and we vary this surface energy in different simulations. And in some cases, we make all particles cohesive. In others, we just make the fines or the coarse cohesive. Now you can see these images for the cohesionless system. So there's no cohesion for a size ratio of 4. You can see after 2 test cycles, we've actually got quite a good quality mixture. And as we increase the number of test cycles, we start to see an increase in the segregation again. It's gone through a nicely mixed state, and then the fines continue to percolate through the bed and the coarse rise to the top. So after 10 test cycles, the mixing index has decreased again. And we can see that on this image here on the right. Now, another advantage of doing this in DEM is that we can analyze this mixing index at any point in time because we know where all the particles are. Whereas in the experiments, we can only do it once the blade is no longer in this vessel. We need to complete a full test cycle so the blade is out of it, and then we can divide each section. Whereas in DEM, you can see we've got data points throughout a given test cycle, and these values here indicate the number of test cycles. So for a size ratio of 4, you can see that we got close to perfect mixing after about 2 or 3 test cycles, and then it starts to segregate as the coarse rise to the top and the fines percolate down. Again, we find that we can use this same mixing relationship to predict the mixing rate based on the value beta. In the DEM simulations, I mentioned we've looked at 2 different combinations of particle sizes for a size ratio of 2. You can see, as you'd expect, as we saw in the experiments, that for a size ratio of 2, there's a smaller difference between the fine and coarse particles, so the mixing rate is slower. There's a slower rate of percolation compared to a size ratio of 4. And when we look at the 2 cases of a size ratio of 2, when we have larger particles, we have a faster mixing rate. And this is really largely down to the fact that we've got a smaller number of particles that need to be mixed, and also there's the essentially wall effects. The geometry size of the gaps between the particles is more forgiving here. There's less chance of friction stopping particles passing through. So for absolute size, if that increases, our mixing rate increases. Now, I did mention that our DEM particles are much larger than the experiments, so we wanted to assess, is this reliable, what we get from DEM? So we looked at this mixing index against test cycles and using this equation to fit the data. If we look at the 2 cases of size ratio of 2, you can see that when we have 2 and 1 millimeter particles, beta is 0.3. When we double the size, beta just slightly more than doubles to 0.615. So then if we take this ratio of absolute size and beta, and we use this to extrapolate the DEM results down to the real particle size, we get the results shown on the right-hand side. So the triangle, the red triangle, is from the DEM prediction of scaling down beta, and the hollow circles are from the DEM prediction for size ratio of 4. And you can see for a size ratio of 4, we get a really good match with the experimental results, but for a size ratio of 2, not so much. We do see it's lower than the size ratio of 4, but not, sorry, these are the DEM results, but it underestimates the mixing rate compared to experiments. Now, I'm not sure exactly why this is. We've sifted the material in advance, but it might be that there's still a slight discrepancy in the size distributions, perhaps. Now, that was for systems without cohesion. Now, moving on to the influence of cohesion, then we've used the cohesion number, which is introduced by Bejani et al. From the University of Leeds several years ago. So based on the surface energy and the Young's modulus, the particle size, the density and gravity, then we determine the cohesion number. And surface energy is the only thing that we're changing between these different cases. Now you can see lots of series plotted on this chart on the right. The hollow circles are with no cohesion. So we saw good quality mixing after 2 test cycles. And then these different levels of cohesion are for different values of surface energy. So a higher value means it's more cohesive. You can also see some cases where we've only added cohesion to the fines, only added it to the coarse, or where we've added cohesion to both. And now if we first look at the case of the influence of the absolute cohesion number, we've got values of 0.025 for introducing cohesion only to the fines. This is for the red triangles. We have it for the fines only, blue squares, with an intermediate value of 0.0775, and then a higher value for these purple triangles, again, introducing only to the fines. So if we compare to the cohesionless case, when we introduce this small amount of cohesion, as you would expect, it means the fines stick together a little more. This means you've got larger clusters that are trying to percolate through the bed, so it slows down the mixing rate. If you increase the level of cohesion, so looking at these blue squares, then of course you get larger agglomerates of these fines. So again, it slows down the mixing rate, and this continues as we increase that cohesion number. Perhaps what's more interesting is if we compare the cases of the same cohesion, but whether we've introduced cohesion to just the fines, the coarse, or both. So this case here, we can see for the green stars, this is when we're only making the coarse particles cohesive. This slows down the mixing rate a little bit, and this is really driven by the fact that there'll be some sticking together of the coarse particles, but not as significant as it would be for the fines, as this cohesion number is not sufficient to make them extremely sticky, given that they've got the larger particle size. But it will mean as they cluster together, there'll be other areas of the bed where there are larger gaps. So this means the fines percolate through some regions faster, but other regions slower, and overall we get a slower mixing rate than we would here. If we look at the case of where we just add cohesion to the fines, then these larger fine agglomerates, as I showed before, these are going to be hampered, their progress through the bed, so the mixing rate reduces. But if we introduce cohesion to all of the particles, where are we? Coarse and fine, then we actually get an intermediate value of the mixing rate. So we get a better mixing if all of the particles are cohesive compared to just the fines being cohesive. And I believe this is down to some of the coarse sticking together and preventing the progress of the fines through the bed. No, sorry, it's leading to larger gaps where the coarse particles have stuck together elsewhere, meaning the fines can pass through more quickly compared to when there's no cohesion with the coarse. Now, what we wanted to do really was a means of predicting what the mixing rate would be based on the particle properties. Our first attempt at doing this was just comparing for the different systems the energy that we've put into the system. And this is the most common measurement done in the FT4 is the flow energy. So it's just determining as this blade moves down through the bed, what is the energy put into the rotation of the blade and the energy moving the blade downwards through the bed. You can determine this experimentally when you use this device, and in our simulations, we've got all the data to determine this as well. You can see when we plot these mixing rates against the energy input, there's some unification of the data, but not all of it. So we need to consider more than just the amount of energy we're putting into the system. And it makes sense that if the system is more cohesive, you would need to put in more energy to get to the same mixing index. So then if we try and normalize the amount of energy we've put into the system by the amount of cohesive energy there is in the system, then this actually leads to a good unification of the data. Now, to determine this cohesive energy, the amount of energy of cohesion in the system, we need to consider the cohesive interactions of each type of particle interaction. So we've got fines and coarse, means there'll be interactions between fines and fines and coarse particles. So we need to consider the total number of particle contacts, or the fraction of the total number of particle contacts between fines and fines, with I representing the fines. Multiply that by the interface energy of a fine-fine interaction, add this to the fine-coarse interaction and the corresponding interface energy, and the coarse-coarse interactions. If we do this, and then we've got our mixing index where we have this power of the flow energy divided by the cohesive energy based on fractional number of contacts, then this is where we get this line showing this unification. Now, this is nice to have a nice unification of the data so that we could predict what the mixing rate would be. However, it was determined by knowing how many contacts of each type we have, which is possible in DEM because we have all the data of where the particles are at any point in time. But in a real industrial case, we won't have this information. So it's not really that practically useful. So then we looked at whether we could approximate it. So now, considering this cohesive energy, we looked at the fractional surface area of each type of particle. So each particle has got a given surface area based on the number of fines and the particles, the size of each of those fine particles. We can determine that total surface area of fine particles, do the same for coarse particles, and get the total surface area in the system. And then we can look at the fraction of the total surface area of the particles that is contributed by these fine particles. If we then introduce this equation where we've got this fractional surface area of the fines squared times by their interfacial energy, fractional surface area of the fines times fractional surface area of the coarse times by that interaction, and then the fractional surface area of the coarse squared, then we get some unification, not quite as good as the previous one, but it looks good enough, and this will be very useful to be able to predict this mixing rate. And importantly, in order to do this, all you would need is the particle size and surface energy information, and then you'd be able to predict this mixing rate. So these are properties that are measurable and could, in principle, be introduced in an industrial setting. So on this first half of my talk on mixing and segregation, just to conclude that the percolation rate increases with an increasing size ratio, and this applies for the initial mixing phase and then the segregation as the course rise further to the top. More cohesive systems require greater energy input to mix, as you would intuitively expect, and we can predict this based on this non-dimensional flow energy, the ratio of the energy input to the cohesive energy in the system. And it's more robust if we use the DEM data of the number of contacts, but that isn't practical experimentally, but we can approximate it. I've got other conclusions here which I didn't actually show data for, but we did also look at the mechanisms for segregation and mixing, and found that the influence of impeller speed depends on whether there's cohesion or not cohesion in the system. So essentially, if there's no cohesion, then particles migrate through the bed, they percolate. If you have a high rotational speed, then you get quite large gaps opening up as the bed dilates. However, the particles don't have much time to pass through these gaps. So the ratio of this vertical velocity of the particles driven by gravity is much smaller than it is. The ratio of that to the horizontal velocity is much smaller for high rotational speeds than it is for low rotational speeds. So you find actually for a cohesionless system, you want a lower speed to improve the quality of mixing. For cohesive systems, it's all about breaking up cohesive clusters. So there, a higher speed introduces higher shear stresses and then breaks this up. Now, you'll have seen in the previous slides, there's a paper that was referenced in many cases. This talks about the details of those mechanisms as well. Now, if I move on to the second part of the talk on dry powder coating. So coatings are important in manufacturing and product development. In pharmaceutical tablets, these are coated to control the drug release and protect against damage and moisture ingress, etc. And powders are also coated to improve flowability. Now, dry powder coating is often preferred over traditional solvent-based coating because it means you don't have to use a volatile organic liquid, so it's got a better health hazard implications. Also, if you use a liquid, you then got to evaporate off excess liquid, so it requires more energy input as well. So dry powder coating is in principle beneficial in many ways over solvent-based coating, but it's not very well optimized. So often people add more coating material than they need to reach a certain product requirement, and they might mix for longer than they need to, so they're wasting energy in that way. So what we aim to do with this project funded by the Engineering and Physical Sciences Research Council in the UK was to develop a regime map for dry powder coating so that we could see the influences of material properties and process conditions and predict how much energy input we needed to control a certain degree of coating. So this research actually, as in the previous research, was all carried out by Dr. Marv Carlo, who's now at AstraZeneca in the UK. So again, in this study, We use the same FT4. Again, we're just simulating it. And we used a shorter bed in this case. So this is a quarter of the normal height in the smaller vessel of the FT4. We first generate coarse particles that we want to coat with these fine guest particles, which are then introduced afterwards and settle on top of the bed. Then we just rotate this impeller at a fixed position, so different to how the FT4 is normally operated. And in different simulations, we vary the size ratio of the host to guest particles, the size distribution, the density ratio of guest to host, the surface energy, and we also look at blade rotational speed, blade design and position, and the percentage of guests that we had and their initial location and fill level. Now, I'm not going to be giving a summary of all of these points, but I will be talking about the influences of size ratio, density ratio, surface energy, and rotational speed. So to quantify the degree of coating, the most common way of doing this is looking at the surface area coverage. So this is the fraction of the host surface that has been coated by guest particles. So this is determined by looking at the projected area of the guest particles, so pi r squared, adding up all the guest particles that are on that surface, and then dividing by the surface area of the host. All information we can determine just based on particle sizes and the number of particles in contact, which of course we know in DEM, we know where we've got host-guest contacts, so we can determine this surface area coverage. We first looked at the effect of particle size. So in these different simulations here, we've got 2% of the bed is made up of the guest material that's placed on top, the finer fraction. And we've got a size ratio where the host particles are 10 times larger than the guests. And we've got this same interface energy. You can see here this normalized surface area coverage. So this is divided by the maximum that could be possibly achieved. So the most we could get to is a value of 1, and in principle would expect to start around 0. However, when we've got the guests settled on top of the hosts, there are some contacts there between hosts and guests. We also find for this cyan colored one, the light blue series, where we've got larger particles. So the guests are 100 microns, the hosts are 1 millimeter. There, even before we start mixing the bed, we get some of the fines percolating through. We've got a size ratio of 10, so if it's not sufficiently cohesive, then they will percolate through quite readily. So this is why you see at time 0, we've actually already determined or calculated a high level of surface area coverage, but they're probably not really sticking to the particles here. And then as we mix, we open up regions in the bed so the fines can percolate more easily, and you can see that it then settles at a very low value of surface area coverage. Now, if we reduce the size of both particles, keeping this size ratio of 10, then we get a slight improvement. We're still probably getting percolation in this case, but then once we reach this region, the green trend, where we've got 65 micron radius guest particles, you're seeing an increase in surface area coverage as we mix. It seems to reach a maximum, then there is some segregation, perhaps that's due to percolation, perhaps the fines are just detaching from the hosts. But we generally, as we reduce this guest size, we get a higher surface area coverage. Now, we wanted to determine what a threshold for when we actually see that coating is occurring. So we just did a crude approximation to start with, where we looked at if we're getting surface area coverage decreasing with time. We said that this is poor coating cases, or probably not coating at all. If it's increasing initially, then these are classed as good coating. Now, in order to take account of the influence of all the relevant particle properties, we determined that bond number was probably the best way of doing this. So the bond number is the ratio of the cohesive interaction that's sticking particles together divided by the gravitational force that's separating particles. We can determine this based on the radius of both particles, the surface energy, and also the weight, which is of course based on density. Now we can determine this bond number just based on the interaction between guest and host. But of course, in this system, we've also got interactions between host-host particles and guest-guest particles. So if we want to account for the bond number of this entire mixture, we need to average out those three possible interactions. And there are three common averaging approaches we can use: an arithmetic mean, a harmonic mean, or geometric mean. And we find actually in the end that in this case, a harmonic mean is most appropriate for this system. So those are the results I'll be presenting later. If I just go back a step, I mentioned this classification of good and poor coating. You can see the boundary between these occurs when we have a guest size of between 65 and 75 microns. So if we determine the bond number for these cases, so this is the boundary, the range where we're seeing a transition from poor to good coating. This corresponds for varying host sizes to bond numbers in the region of 160 to 212. This is just based on the guest-host interaction. We could also determine bond number based on the arithmetic mean, harmonic mean, geometric mean, etc., and we'd get different values, but the principle is the same. We find a threshold where we want to exceed this, we want a higher bond number than this to ensure that we're going to get good coating. We next looked at the effect of density ratio. So in this case, the guest particles are equal to or more dense than the host particles. You can see with a density ratio of 1, then before we start mixing, they all settle on the top. Density ratio of 4 for this same interface energy means that that cohesion is not sufficient to stick the particles very well. So this is why we get this initial percolation that I referred to on the previous slides. Now again, looking for this interface energy, this is for host sizes of, I think, 50 microns, although I didn't include that on here. You can see with a density ratio of 1, we're getting a nice surface area coverage change, and after a couple of blade rotations, we've effectively coated very well. As you increase the density of the guests, then this interface energy is less significant, so it doesn't allow the particles to stick. So we see we're dropping below that threshold, so we're not getting good coating anymore. Now, if we look back at the boundary we mentioned previously, this threshold bond number of 160 to 212, that's where we want to be. You can see, yes, so this is the particle size we use, the guest size of 50 microns. You can see with a density ratio of 1, our guests add the same density as our hosts. Here, the bond number in that case is above this threshold. So we would expect we would get good quality coating, as we saw on the previous slide. For a size ratio of 2, the guests have got double the density, so they're just inside this boundary. This is why we see that there's a still reasonable coating, but it is dropping off significantly towards the end. And for higher densities, we're below this threshold, which is why we're not getting very good coating. So it seems for size and density ratio, this threshold seems consistent. We then looked at different cases of size ratio and density ratio. We can directly calculate what the bond number would be. So bond number increases downwards and to the right, and this threshold is shown here by the black lines. The dots on these charts show the surface area coverage we determined from different simulations, and you can see this is surface area coverage. Yellow meaning it's in the good range, green it's okay but better than blue. You can see that in these cases, when we're above this threshold, we do get an improvement in the surface area coverage. We also looked at the effect of surface energy. So if you look at the plot on the top left, we've got these 5 values of surface energy increasing from black to green, dashed black, red, and blue. You can see for this density ratio of 1, as we increase this interface energy, this means the fines are more cohesive. You need to mix for longer to break up these cohesive clusters of fines before you can get them to be directed to the hosts and stick to the hosts. So we get a slower evolution of this increasing surface area coverage. It does suggest that in all cases, we would eventually reach this maximum theoretical coating, but after 5 rotations, that's not enough to see it for this most cohesive case, but it's moving in that direction. But yes, if we increase interface energy, the mixing rate slows down. If we then look at the extreme case with the density ratio of 4, for our initial interface energy, the lowest value, as we saw previously, we don't get effective coating. This surface area coverage decreases with time. We increase to an intermediate value of 86 millijoules per meter squared. We do get an increase in surface area coverage, but then it drops off. And then at the highest interface energy, then we do get good coating that looks like it's going to remain stable. So the mixing rates and the surface area coverage we achieve depends on size ratio, density ratio, and interface energy, which can be accounted for with this bond number. We also did similar plots of the density ratio against the size ratio for different values of interface energy. And in all cases, if we're above this threshold, we see that we calculate a high surface area coverage, as we would expect. So that's the influence of material properties. But now if we want to develop a regime map, we've got to think about the process conditions we've used, the impeller speed, the mixing time, etc. So a way that we use to quantify this is the Stokes deformation number. So this is the ratio of the mixing energy to the cohesive energy, which is essentially what we looked at in the previous part of my talk on the mixing and segregation study. The mixing energy is just directly determined based on the torque acting on the blade and the degree of rotation. It's given by this first equation here. The cohesive energy, we've determined it in the same approach that I talked about in the previous part of the talk, of the simpler approach based on the fractional surface area, as this is something that can be implemented industrially based on the size and surface energy information. So if we look at the ratio of mixing energy to cohesive energy, this gives us the Stokes deformation number. So what we aim to achieve in developing a regime map was to plot this Stokes deformation number against the bond number. This is essentially showing process parameters and material properties, and we can use a color scale for the surface area coverage to complete a map here. So to do this, we needed to run several simulations. We used a design of experiment approach using this subol sequence for 32 different simulations. This sequence just tells you when you put in your maximum and minimum values of bond number and impeller speed that we want to use, it tells you the best combination of those values to use. So for any given simulation, from this we determine what the impeller speed is. We decided to look at 3 different size ratios of 10, 20, and 30. And for each of those, we looked at density ratios of 1 and 1.5. And then based on the particular speed and the bond number we needed to achieve based on this sequence, then we just varied the surface energy to get that required bond number. So then we've got this combination of 32 different simulations that we ran. When we do that, then on this plot of Stokes deformation number against the harmonic mean of bond number, each vertical line is one simulation. So it's got a fixed bond number as it's just based on the material properties used in that simulation. Initially, the surface area coverage is low, but then these data points are for increasing time steps. So as we put in more mixing energy, the surface area coverage increases because our Stokes deformation number is increased. Now we can interpolate in between the results of these simulations and get this map here on the right, which we can then apply some smoothing to and add some boundary lines for every 0.1 interval of surface area coverage. So this map tells us if you measure your material properties, you can determine your harmonic bond number, harmonic mean of bond number. And then that would tell you, for example, if we have a value of 15, we want to achieve a surface area coverage above 0.9, then we need to put in at least this amount of mixing energy. Now, if we know the torque acting on the impeller, then we can determine how long we need to mix for in order to achieve that level of surface area coverage. So this is to help aid industrial applications of dry powder coating so that you can minimize the energy input to get the product requirements. Now, what we then wanted to do, as this was all based on experiments and all based on simulations and all at small scale, we wanted to see whether this worked in a larger scale system. So I'll just go over these last few slides as quickly as I can. We looked at a helical ribbon mixer working with Johnson Matthey in the northeast, not too far from Newcastle University. Francisco was carrying out this work. He's now working for Johnson & Johnson in their pharmaceutical section in Belgium. He was mixing zeolite as the host powder with fumed alumina as the guest. Now, the zeolite itself is very small. It's just about 3 to 5 microns, and the fumed alumina is about 100 nanometers. So we'd got a size ratio above 10. We actually impregnated this zeolite with iron oxide to give it a distinctive red hue, a red color, meaning we're mixing it with this white alumina. So then we could use colorimetry to quantify the quality of the coating. We also used the FT4 to measure the flowability of different mixes and used SEM to analyze the surface area coverage. So within this ribbon mixer, we looked at 3 different impeller speeds, 4 different mixing times. Now, what we intended to do was to fit the data we get onto the regime map that we just developed. However, once we started the experiments, we found we couldn't actually measure the torque acting on the impeller. So that was a reason we couldn't determine the mixing energy. And furthermore, the equipment wasn't available for us to quantify surface energy either. So we couldn't find any point on either of those axes. So instead, we ended up just analyzing the influence of impeller speed and mixer time. Now, one thing to bear in mind is we've got 4 liters of powder in this vessel, and we want to do tests using much smaller quantities of powder. So we used a rotary sample divider to split this down into 8 different smaller volumes. We took half of each of those and then combined them and then split them again into 250 ml containers so that we've got a more robust and consistent sampling of this whole 4-liter container. And then half of these were used for flow analysis, and the other half we used for colorimetry and SEM. In terms of flowability, and looking at the influence of mixing speed, we did this in the FT4 looking at the basic flow energy. So this is measuring the resistance to flow. So a higher measurement means that the powder is more cohesive. A lower value, it's more free flowing. You can see the uncoated powder initially has a value above 300 millijoules. As we then coat the material after mixing for 45 minutes at different speeds, then the flowability improves, which is good. That's what we're intending to do. And we actually see there isn't that much difference influence of impeller speed, but actually the lowest mixing speed gave the best improvement in flowability. Now, if we consider flowability based on the shear cell analysis at 3 kilopascals, we don't actually get the same trend. In all cases, it's worth noting this is the flow function coefficient. So a higher value means it's more free flowing. In all cases, again, the mixed powders, the ones that have been coated, have got a better flowability than the uncoated zeolite. But in this case, we see that higher impeller speed gives a better flowability. Now, it's worth noting that shear cells are measuring the onset of flow, whereas the basic flow energy is a dynamic flow measurement. So it's looking at when the material is moving. So it's not that unusual to get different trends. They've got different meanings, these measurements. The influence of mixing time, just using this intermediate impeller speed, you can see that we found an optimum mixing time of 20 minutes. If we continue to mix further, the flowability worsened, and we're not really sure why that is. And it's worth noting But that is not something that was predicted in our regime map in the simulations. There we just saw more mixing energy, better surface area coverage. So this suggests that it's actually more complex than our map is suggesting. And likewise for the shear cell test, we found this same trend, that mixing for 20 minutes was optimum in this case. So there's still some more work to do to understand why that is. Looking at colorimetry, we'd expect that if we've got no guests in there, we'd have a deeper red color. As we add more guests and they stick to these host particles, the color should be lighter. Our colorimetry on this plot here shows the different cases we've got. If we zoom in to see the differences a bit more clearly, and note that the uncoated zeolite is shown by this circle here, and the star is the alumina that we're coating onto the zeolite. What we would expect is to see all measurements where we mix these two to lie along a line connecting these 2 points. But that's not what we see. And we see very little discrepancy between these. So again, this is something else where we need to do some further analysis to try and get a better interpretation of this. I don't know if it's down to the equipment itself or the way that we've interpreted the data, but this is not really matching what we'd expect to find. One thing that did turn out to be quite successful was analyzing the surface area coverage by SEM. So here we've got the host particles that you can see have got a very distinctive cubic shape, and you can see some guests coated on these surfaces. This is at the lowest speed and the shortest mixing time. We actually used a function in ImageJ, a trainable Weka segmentation, which is using machine learning, where you identify what you class as the host material. We identified those with this red color, identified the guests as the green color, and identified the background as this purple color. And by picking lots of points and saying whether this is host, guest, or background, then you can get the machine learning algorithm to analyze the image and tell you what all of the image is made up of. So this gives you a probability map saying that if it's white in this case, then it's 100% confidence that the pixel is a guest. If it's black, then it's definitely not a guest, and anything in between would be varying degrees of confidence. But you can see that everything here appears to be black or white. So then, based on determining how many pixels are guests and how many are not, then we can determine the surface area coverage. So we selected a number of different host particles, those that are preferentially front-facing of the image, and analyze the surface area coverage on each of those faces. And when we did that, we found that the surface area coverage, comparing the 3 different rotational speeds after 1 minute and 45 minutes, in all cases, if we mix for 45 minutes, the surface area coverage increased compared to 1 minute, and increasing impeller speed led to a better surface area coverage. Now we do see surface area coverage, we see a difference after 20 minutes. However, this is showing that after 20 minutes, we've got the smallest surface area coverage. Now that would intuitively suggest we would have the worst flowability, but that's the opposite of what we saw experimentally. So we need to do some more deeper analysis on what's causing that discrepancy there. So to conclude, from the regime map, we predict that surface area coverage increases with granular bond number and with mixing energy. Our pilot scale experiments show that surface area coverage generally increases with mixing energy, both in terms of time and impeller speed. However, we find that there appears to be an optimum that is not picked up by a regime map. And some of the flowability analysis agrees quite well with the surface area coverage, but not all of it. So challenges we faced, as I mentioned, it turned out we didn't have a torque sensor, so we couldn't determine the energy input. We get batch differences in colorimetry, and we were unable to characterize the surface energy just because we didn't have enough time in this short project. We didn't have the equipment available. So that's something that we can still do and intend to do later. We did try simulating this to develop a regime map specific for this case. However, due to the size of the geometry and the small powders, that really wasn't feasible. So just to acknowledge the funding that was provided for this, Johnson Matthey for giving access to this ribbon mixer and supporting and providing the materials. If you want to connect with me on LinkedIn, there's a QR code to my profile here, and I'm just happy to discuss any interest you've got in this line. And also, if you're interested in using this ImageJ trainable Weka segmentation, then there's also a link here that you can use. Okay, so thank you everyone for your attention, and I'm happy to answer any questions.
Yeah, thanks a lot for Collins. They're very good. Their presentations. Actually, you give us a lot of their work, yes, including the experiment work and also simulations. And regarding this coating and particle energy. Actually, I'm not very familiar with this, but I have I'm very interested in your some issues. Now, some question actually in the Windows, and I'd like to ask just repeat ask you one by one. And the first question actually from Kadiri, how much mixing do you do? Sorry, yeah, just for your.
So, Mr. Arbour, were you referring here to the case where we pre-mixed and then analyzed whether it's segregated? Is that what you were looking at?
Yes, Colin. I was thinking, I mean, later on I realized that you do a number of tests. So that means the number of penetration and withdrawal. So I got that. But in calculating the work that you do for that, do you actually take account of the work when the impeller is moving up?
Yeah, I'm sure we did. Yeah, I didn't actually include that on the slide, but yeah, I'm sure we did include that as well. Yeah, it's not something that the device would directly give you, the energy of the upward movement, but it gives you the torque, so you can determine it from all that data, yeah.
Yeah, I also, when you were presenting this, it just occurred to me that Vincenzino Vivacqua did a nice piece of work for his PhD on segregation in fluidized beds. And he's got some very nice correlations on basically regime map of segregation. And I just wondered whether his correlation is also applicable to FT4 operation.
Oh, interesting. I'll have a look at that.
Yeah, there is. He's got some nice correlations on, but I don't think he's looking at the cohesion, but looking at different densities and sizes.
And presumably varying the fluid velocity as well.
Yes, indeed. Yes, I think so. Yeah, and yeah, and thank you very much, Colin. Very, very nice talking this. Fantastic. Thank you very much.
Thank you.
I need to talk to you about quoting later on.
Okay. Okay.
Okay.
Shall I carry on going through these questions?
And yes, and another question actually from Professor Lan, and his question is that what is the physical meanings of Stokes deformation number? Yes, okay, so I also have some question here.
So it's just simply the ratio. It's a dimensionless number, as we like in chemical engineering. It's the ratio of the energy input to the resistance, the cohesive energy. At least that's how we've determined it. Perhaps there's another more precise definition I'm unaware of, but that's really what we interpret it as.
This number actually is very popular, used in your area to describe the energy.
There is also, I think, one of the most commonly known regime maps is one for granulation from Jim Lister, I think, and his group from over a decade ago, and that also finds that Stokes deformation number is one of the axes. So yeah, it is a very important one when you're dealing with cohesive powders.
Okay. And actually, I have another question, not right here. Yes, Kadiri also know my areas. Yes, I am very interested in the electrostatics because from your case, I'm thinking the particles is very dense, and the particle and the particle walls interactions will cause electrostatics. So, do you consider the electrostatic effect on the energy of the particles, yes, as you run in your experiment or your simulation or your theoretical work? Yeah,
it's not included in the simulations. No, and that is, that's something that's quite difficult to model and quite computationally expensive to model.
Yeah.
In terms of the experiments for the first part of the study, we were using sufficiently large glass beads that I don't imagine electrostatics was an issue. For the pilot scale mixer, though, perhaps it would be. Yeah, because then we've got very fine material. The
Yes.
fumed alumina is incredibly low density, about 100 micron particles, and I think it's really got a packing fraction of about 4 or 5%. It's incredibly light and fluffy. Actually, the scooped volume we put in, although we only used 2 weight% of the fumed alumina, I think the volume we put in was almost the same as that of the hosts, just because it's such low density. So I expect that is very prone to electrostatics. Though I must say I didn't actually observe it experimentally, didn't observe any electrostatic behavior.
Because just now, from your presentation, the PPT, you give a movie of the particles in surrounding the rollers. I realized some particles actually click on the wall, on the window, on the pipe walls. So I'm guessing maybe this is some due to the electrostatic effect on
I
it.
think that was probably cohesion, really, rather than electrostatics.
The picture, you see some particles, stick along the walls. So I just know this is actually very popular problems in the particle or on the powders. Is your work, actually have done a lot of their stuff in the energy and the surface, and very good actually. And I will transfer Colin, can you please give us your PDF of your presentation stuff later?
Yeah, that's no problem. I'll send that to you.
Yes, no problem. I will, distribute your stuff to all of this, my friends and colleagues in this IMFTF and their groups.
June, may I ask you? May I ask Colin a final question?
Yes, please. Ask me. I'm Colin.
Yeah, Colin. Colin, what are your thoughts on input power? Referring to the question that Nan had about implication of Stokes number. Thinking just about energy, then of course, if we are going to compare the thing, maybe we need to also take account of the power rather than total energy. What is your thoughts on that?
Yeah, I guess if you're operating in the same regime, energy might be enough. If you're in the same regime, then it could be the case that the energy is being used as effectively, even if we change the speed. So that is all that matters. But I think if you're seeing a significant change in that flow profile, one case is not going to be using the energy as reliable as another. So, as effectively as another. So energy alone probably isn't sufficient. If you've got significant differences in impeller speed, then I think speed itself is going to matter too. And that probably does come down to the power, might be the better way of representing it. But power alone probably isn't enough. You do need to consider the total energy too. So then that adds a third scale, which makes things more complicated. But that is particle systems, I guess.
Thank you.